As you all know that this is your first control course. Control engineering actually, like power engineering, like electronics engineering, communication engineering, you must take several courses to be specialized in that specialization. You need to take more courses. This course is considered as the starting point of control engineering, and I call it just the basics, just scratching the surface. We just enter the field, okay? So everybody actually needs to take this course, starting from engineering students, going to the people working in business, for example. And I will give you examples about control applications in business, in finance, and so on and so. And this lecture actually, I put 3 goals. First of all, I'll give you an introduction and the course structure and administration. Administration here means how we are going to work together, okay? Then I'm going to define feedback, control systems, and then how to recognize the main feature. كيف نتعرف على control systems. Third, describe what control systems do and the primary principles of control. This is actually very important, and it will be at the end of the lecture. You need to know how we use the control in real life, in applications. So I am giving you so many examples so that you can understand the topic actually and what you are facing. الكتاب اللي راح نستعمله هو كتاب ديازو، طبعا مع 2 مؤلفين، اسمه Linear Control System Analysis and Design. حلوة هاي. بعدين بنروح على نعم على هاي الحلوة في الموضوع انه صرت تعرف على الليست. شو before we start actually with the 3 goals, I would like to introduce the course syllabus to see what the topics are and what the skills we are going to عن جد اني صرت اعرف. Okay. In this course we are going to meet each other in 44 lectures. There will be projects, about 30 hours that you need to work at home, not here. So I usually give homeworks and projects so you can work them out at home. There will be other things like homework and 14 hours of others. These calculations actually are for me to see about your workload and how much you're going to work at home for my course, okay? And you will see that you need these much hours. So totally you need for this course 106 hours, including the lectures and what you're going to do at home. This is the minimum actually. I'm not going to talk about the course content because it's going to be actually like puzzles for you. You will not understand things, even the concepts here you don't understand, just words. Most importantly actually is the learning outcomes. This is very important, okay? This is what I expect from you at the end of the semester, okay? So I expect from you to be able to, I need you to understand the word able. Able, something that I can test. I can put you into exams, ask you, can you do something, okay? So these are ability things. First of all, I would like you to be able to apply knowledge of calculus, differential equations, linear algebra, complex variables, and so on and so. So most of the courses you took in calculus, mathematics, I need them here. And this is actually maybe the first course that you need all these topics together. And I'm going to test you in this. So in the exam, I'm going to deduct marks for your mistakes in calculus, because calculus is put in action here, okay? So without the calculus, this course is useless. 2, ability to design control system. So I'm going to introduce steps in order for you to be able to design a system to meet specified requirements, not just any system. We have to put specifications, then you start solving the problem, designing the system until you meet the specifications, okay? Third, ability to identify, formulate, and solve control systems problems. Identification and formulation, again, is very important because it's not always in real life that somebody gives you a well-defined problem. Never. This is actually just theoretical part. In the university, you just take problems, well-defined, everything is given, just you solve it. In real life, you don't have this. Okay? In real life, you have to formulate the problem. You start listening to the people, putting things in words, then putting things in engineering context. After that, you start solving the problem. After you define the problem, is it, for example, power problem, electronics problem, programming problem, and so on and so. Okay? So identifying the problem is very important. 4, we will be using techniques to be able to design systems. Some of these techniques, actually, you know them. For example, the BOD technique, you know the BOD technique, where you use this technique in signals, electronics, body plot. You plot the magnitude and phase. Minus 20 dBs per decade, something like that. Okay. Root locus, I'm going to introduce it in this course. It's a technique, very important technique in control. Nyquist, state variables, and MATLAB. I think some of you have learned about MATLAB. Even if you haven't heard about it in this course, you need to understand something about MATLAB and the application in control. Okay, so in this course, you are supposed to be able to do these 4 things. Okay, that's all. This is what I'm expecting you from this course. To be able to do these 4 things. If you fail in some of them, okay, then you fail the course. If you are not able to design a system, then you fail the course. If you don't use calculus and mathematics very well, then you will fail the course. Okay, so you must be able to work out the 4 things here. Okay, maybe you cannot reach the level of experience, all of you the same level of experience, but some of you will be excellent, some of you will be very good, some of you will be good, but anybody below good, he will fail this course. Okay, this is how I evaluate control course. Okay, now the textbook, I'm going to use 2 textbooks. This semester I switched them according to priority. First textbook is the first one is the textbook, and the second one will be your reference. Okay, so if you need this textbook, you can find it here and there, and you know how to define it. Now, next we go to the assessment. In the assessment, you know, 40 points for the midterms, 1 and 2, 20 each. Then we have 10 for the homeworks, 10 for the projects, and 40 for the final exam. Okay, so I don't want to encourage you to study for the first and second midterms or for the finals, because usually you do. But I want to encourage you to work well on the homeworks and the projects, because these are 20 points. Yeah, that's right. But if you do them well, you will get hundreds in the finals and hundreds in the midterms. Okay, so it's very important if you work with me on the homeworks and projects. That's it. To reach these, to reach these goals, not the goals, sorry, to reach these skills, okay, we have to cover these topics. You will not just sleep and go and wake up in the morning and you find yourself being able to do these 4 things. Okay, I need to introduce topics to you so that you can do this, or you obtain, or you earn these abilities. Okay, so there will be mathematical modeling, review of Laplace, introducing feedback. Then we go to midterm 1. Then we introduce root locus, and so on and so on. Okay, I'm not going to just read them for you because this is not the way things are done. Okay, we will go back now to our PowerPoints. Okay, now we have just talked about the goals of this lecture. I have introduced or talked about the course administration, how the course will be, how we'll proceed in this course. Next, what is feedback? You see, I haven't started with what is control systems. I started with feedback, because the feedback is one of the most important concepts in control systems. If we don't have feedbacks, then actually we don't have a real system. Okay? For example, you tell somebody to do something. If you don't track him to see if he has done what you ordered him, then he may do it or may not do it. Okay? So when you order a system or somebody to do something, then you have to keep an eye on him, watch him, and if he do it well, okay, then perfect. If he doesn't do it well, then you have to adjust him and tell him to do it better. And this feedback goes on until he gets 0 error. So we need the feedback. So Maria Webster in 1920 put some words about feedback. She said at that time that the return to the input, we take some part of the output, like a sensor. We don't take the whole output to feed it back. We just sense something, okay, of a part of the output of a machine, system, or process. So we are going to control process, machines, or systems, okay? As for producing changes in an electronic circuit that improve the performance, or in an automatic control device that provides self-corrective action. So here we have a system, okay? System 1. It gives an output. Then from this output, we feed it to the second system. And this is what we call a feedback. And then it goes to the first system. Okay? So we have a process. We have a sensor that measures some value that we want to control. Then we feed it back. Of course, this is not a complete system, just to give you a clue about it. Feedback equal to mutual interaction. Mutual means one affects the other. Not just one-way system. Both systems work together in coherence. You have heard about mutual inductance, for example. You know, one inductor affects the other inductor, and the other inductor affects the first inductor. So it's a mutual interconnection of 2 or more systems. System 1 affects system 2, system 2 affects system 1. Cause and effect. I mean, which one affects on the other one? It's a tricky part, okay, because both of them affects on both of them, okay? One affects on the other one. So we cannot define very well the cause and the effect. So systems are mutually dependent. Feedback are everywhere in nature and engineering systems. This is a claim, and I have to show and prove that control systems are everywhere, okay? Actually, most of the systems are control systems. Then I'm giving you 2 examples. We have a tornado, and we have a Boeing 777. What do these 2 have in common? Okay, you can think of something. What? They are highly nonlinear, complicated dynamics, not easy to put them in mathematics, I mean. Both are capable of transporting goods and people. Yeah? So this is what they have in common. Okay? But one is controlled, and which one is that? Yeah, the airplane is controlled, otherwise nobody will fly them. So one is control and the other is not. Control is the hidden technology that you meet every day. It heavily relies on the notion of feedback. Okay, so the airplane actually is a controlled machine, I can say, and it has a lot of feedback signals. Even you know that some planes that can drive themselves. You see, planes drive themselves, and sometimes you hear this word autopilot. Autopilot. You just put the plane on autopilot, and it control and adjust itself. So it has a lot of signals. You don't need a pilot to drive a plane. Okay. So this is just a hint. Example: we have something called flyball governor. Look at the date, 1788. A scientist has to think of how to control a steam engine. You know, for example, if you have something on your shoulders and you are running, your speed will be slow, okay? If you take some of the weight of your shoulder, your speed will increase. If I put more load on your the speed will decrease. So this is the same story with engines, with motors. Okay. So this engine, of course, here's the structure. This engine, we need to control its speed. Okay, and this is a steam engine. It works on steam. So in order to control the speed of the motor, sorry, the engine, he introduced what we call a governor. Okay, this is what we call a governor. These two balls, we call them flying ball. Okay, as the engine rotates, this by centrifugal force go like this. Okay, they go like this. When they go like this, they fly up. As they fly up, they control a valve here, which is responsible, for example, for the fuel going into the engine. So as the speed of the engine goes beyond the threshold that they want, it must close the fuel, so the speed goes down. If the speed goes down, the balls go down and the valve opens, and so on. And this worked for in one mill factory for 102 years. This machine worked for 102 years before they put it into museum. That was the first feedback system. It is self-controlled. It controls the speed by these two flying balls. Okay, you can understand there is a bolt here attached to the shaft of the engine. As the shaft rotates, these two balls goes up, closes, controls the valve here. Okay, so that was the first, for example, the first sensor, I may say, the first sensor of the speed. All of you, I think, have taken machine course. Okay, there is in machine we use something called tacho generator. We measure the speed so we can control the speed by tachometer, okay, or encoder or something. Okay, so here what we have, steam engine controlling the fly ball governor, and from the fly ball governor goes back to the steam engine to control, of course, the steam engine. Okay, this is an image of the machine in action. You can see the chains here connected to the disc, coming from the shaft, flying wheels. Here's the ball, and it worked. Okay. Other examples. We have examples in biological systems. Your system is your system, our human system. Okay, is a very strict control system created by nature, by God, of course. Physiological regulation. What we call, there is a term here called homeostasis. This word means that when your system, for example, or your body is being exposed to low temperature or high temperature, your body exposed to high or low temperature, internally it starts to adapt itself to be able to live in that temperature or in that environment. Okay, so when you first go, for example, into a country where it is very cold there, you will suffer a lot. But after a year or two, you will find yourself that you are comfortable living there. Otherwise, you cannot stay there. So your body internally starts to adapt itself to live in that environment. Another thing is from financial systems. It's a very important application, or it is actually very important application. Markets and exchange. Of course, you know the meaning of exchange, البورصة. Then we have supply and service chains. Supply and service chains. For example, I can give you something you can understand. You have a shop, a supermarket. You bring so many goods to sell in your market, and some of these goods, there's a high demand on some of these goods. Okay, high demand. As the demand increases, you watch your shelf that the products are going away very fast, then you have to ask for the new goods, isn't it? Some of them there is less demand on them, you don't bring them. What you are doing here actually is a control system, okay? You monitor the demand on your goods or merchandise, and you call for more merchandises or more goods, isn't it? Okay, so now there are other systems, automatic systems. You know the barcode? When you go to a supermarket, they charge you according to the barcode. Now there's a software there where the software monitors the stock and knows exactly how the demand is, and you can plot curves to see which merchandise is more demandable, isn't it? And the system itself can put orders for delivering new goods. Okay, you don't have to go traveling between the shelves to see which products is missing and which product you need to take more, and so just the software will monitor everything. At the sale point, you just whatever goes out is deducted from the stock. When it reaches a threshold, then the system itself can put an order or just give a command to the manager. Okay, now we have another application, which is the driver himself. You as a driver, when you are inside a vehicle, okay, you actuate. You step on the pedal, fuel pedal, gas benzene. Okay, according to what? Think about it. Maybe the sound coming from the engine. Okay. Maybe from the type of the road. Okay. Maybe you have traffic in front of you. You decide. Okay. You monitor things. So you sense. Okay. So you are the sensor now. Your body, the whole body is a sensor. Maybe there is no danger in front of you, but you are afraid. You just lift your foot from the step, isn't it? Because you are afraid. Sensing, then you make some computation. You compute. Actually, you don't compute. You just analyze. You think. Then you decide what to do. Okay? But you think. If you don't think, if you don't have what I can say, if you are crazy, for example, you are not allowed to drive. Why? If you don't have the good mentality, then you cannot drive. You can actuate, even if you are crazy, then you can actuate, isn't it? You can see and hear and everything, but you cannot analyze the data coming. So I need a computation. I need a processor to process the input. Then I can decide. Now, from this simple idea, they started to build unmanned vehicles. Unmanned vehicles. Vehicles that drive themselves on real roads. And imagine how complex it is. Yes, Google. But Google used the GPS and GPS location. And also you need sensors around to see if there are vehicles here or there, somebody crossing the street. Yeah, I know. But it depends on the environment. Okay? If you put it in the center of Nablus, for example, it will never drive 1 meter. Okay? It depends on the environment where it is being driven. Okay, so the goals here of this system that you are thinking about is stability, performance, and robustness, and we will talk about this. I'm not going to talk about them now. I have to finish these. Another example about what we are going to expect in this course is that you have a DC motor. This motor, I'm calling it design example. This motor actually here, okay? To one end of the shaft of the motor, attached a disc, rotating disc, okay? And of course, this motor, you can't simply just give it, this is a motor. You know how it works, okay? If you give it voltage here, the motor will rotate, isn't it? It rotates. If you change the polarity, it will rotate in the reverse direction. Simple. This motor is driven by an amplifier because sometimes the controlling signal is low, but the motor needs high power signal, so I need an amplifier. Okay? So from here, if I input a voltage, from here, if I remove all these and input a voltage, the motor will rotate, isn't it? Okay? And we call it open loop system. Now, if we attach here what we call a tachometer. Tachometer is a sensor. It's a very small motor. I will say motor. But you know, if the motor, you know the difference between motor and generator. Motor converts the electrical into mechanical. Now, if you have the mechanical, then you will have electrical. Okay? So this is exactly what we have here. The shaft of this device is connected to the shaft of the motor. The motor is driven from this side. Then it is rotating. Then it rotates the rotor of this device. Voltage will be generated. This voltage is proportional to the speed. Okay? Maybe small, but I don't care. Okay? But I have a voltage proportional to the speed. I compare it here. You see there is a negative sign here, a positive sign here. So we have now here the error. We don't have the actual voltage. We have the difference between the required and the actual output. Okay? So we compare here, then we have the error, and accordingly. You see your input, it's coming from a battery with a variable resistor. As you play with the variable resistor, you play with the voltage here. Okay? Then you change the voltage here. Then you change the velocity. This is a very simple system. We can put it into block diagram as this. We have the desired speed. Of course, the only way to input for the time being is by inputting the voltage. So we have the input voltage. We have the actual speed. If the actual speed, for example, is 1,000 RPM, this 1,000 RPM is converted through the tachometer into voltage. Let's assume that it corresponds to, for example, 10 volts. And the desired here is given by voltage as a 10 volts. This means that the error is 0. Now, I'm not going to get into this block right now, but assume that you change the voltage from 10 volts up to 12 volts. Okay? From 10 to 12. What will be the difference here? 2. Now the motor must respond to this change in error. So it must increase the voltage, increase the speed. Smooth, of course, exponentially, because you know it is an RL circuit, until it reaches what? 12 volts. Simple mechanism. Okay? So we have feedback. We have the control device, what I call amplifier. We have the actuator, what we call the DC motor. Actuator, something that performs your job. Okay? Your hands are your actuator. But sometimes your hands are your sensor also. So you can use them both to do the job or to sense something. Okay. The process is what are the purposes of this system? This is what I call the process. The purpose of this system is to rotate this disk, isn't it? So this is the process, and I am monitoring the process. So I have my eyes in here, okay? I'm just watching this. Of course, not by my eyes, by the tachometer. Okay. So this is what I call a design system. Of course, you can build it directly and construct the hardware. This is a modern feedback control system. Of course, there are so many blocks in here. Basically, we have the same, but we have introduced what we call noise. You have heard about noise in signal systems. Noise is a very disturbing signal. We don't like noise. Okay, noise is something bad. Okay, we have to get rid of it, but of course we cannot. You can imagine an airplane flying in the sky, and another airplane is coming around with a high speed. It would affect the movement of the first airplane, isn't it? We need to readjust ourselves. Okay, and so there are so many sources of the noise, but here in this system we have to include them into our system so we can analyze them. Okay, you can see in modern control system we have what we call analog to digital converter. We have digital to analog converter. When you use a computer, for example, to control a system, or microcontroller or microprocessor, you have to get your signals inside the processor digitally, and after the processing you have to get it out analog, isn't it? So in control systems, actually there are many new things we have to take care of, according of course to what we have coming from the computer world. Okay, as the computer and the processing capabilities increases, this will positively affect the control engineering. Okay, we need everything they do in computer. Two main principles of control. The first is robustness. Robustness to uncertainty through feedback. Robustness, which means the system must be able to quickly adjust itself, or it should not. This is more simple. The system should not be affected easily by external disturbance. You see what I mean? The system must be robust. For example, the Palestinian society, is it a robust society in terms of political issues, political disturbances? Is it robust? It is robust. You hear everything every day, a lot of things, disturbing things in the news, isn't it? But most of you never even think about it, isn't it? No more. But if these news suddenly, okay, here the same news here in Jordan, for example, you will not find anybody in the streets, because the people will be disturbed, because they never faced such problems. Okay, so they will be curious, they will be anxious, they will be afraid, they will stay at home. What's going to happen? The stock market will be changed, everything will be disturbed. But here in the Palestinian society, because of the years of experience with the, okay, we are robust. Not everything actually disturbs us. Okay, so this is what I call robust system. Your vehicle, your car, if it's an old car, for example, you won't even care if somebody hits it. Okay, because it's robust. We all believe that. We say that it's built from heavy metal and it's not affecting, it's like a truck and so on. But the new cars, okay, are in that, from that point of view, are not robust. Okay, so this is what is important. The system that you will design must be robust, not easily affected by the external disturbances. Okay. Design of dynamics through feedback. Feedback allows the dynamics of system to be modified. Example I'm giving you about stability, augmentation for highly eagle unstable aircrafts. Okay, as I said, a few things, sometimes I talk more, others I just skip. You will read them. I will give you the photocopy. I will give you a handout so you can read them at home. Cruise control. This is actually how we can control a vehicle without a driver, if we want to do that. Okay, I'm giving you some ideas here about robustness and stability of the system. There is a mathematical model here. This is a mathematical model of the vehicle. You can see there is v dot, which is the first derivative of the velocity. Anyway, this is a first order differential equation. You have the U engine, the input coming from the engine. Okay. Anyway, let's have a look at this curve. That's all I want to show you. okay, you will notice that the actual speed of the motor, this is the actual speed of the vehicle, is a function of desired velocity, the desired velocity. I need this vehicle to go, for example, 65 miles per hour or 65 kilos per hour, okay, kilometer per meter. So it is the output speed of this vehicle is a function of the input, your command, your required speed, and the input coming from the hill. You know, the street, sometimes there are hills in the street, there are bumps in the streets, there are holes in the street, okay? So this force coming from the street, it depends on the type of road, okay? So what we can see is that the speed of the motor is increasing, okay, increasing until it reaches or goes into what we call steady state. Steady state. When it reaches the required speed, which is here, okay, this is our required speed. When it reaches the required speed, it must go into steady state. And when it goes into steady state, it should not be easily affected by disturbance or external inputs. We can see that actually. As k, for example, here in this term, as k goes to infinity, what will happen to this term? Think. Actually, it is written here, but you have to see it. It is k over k, isn't it? Infinity over infinity. You have to apply L'Hopital rule. Okay? So it's 1. What about this one? As k goes to infinity, I mean large k, it goes to 0. What does that mean? The effect of the disturbance coming from the road, you see, the effect of the road on the response of the system is 0. Of course, when? If k goes to infinity, or large k, isn't it? So the disturbance here has minimum effect on the response as k goes to infinity. This is kind of control. You have to see what things that affect your response. So this system in that sense is what? Disturbance, rejection. Yes?
K, what represent K?
Oh yeah, of course, you don't know what's K now, okay? It could be the gain of the amplifier inside, it could be anything. We will talk about K.
Okay.
K here actually, we call it gain factor, okay? And we will see a lot about K, okay? I'm just giving you some mathematics to think about now, okay? You actually don't know anything about this formula and from where it came. So there is something here that says that if K is very large, this term will go to 1, okay? And if this is very large, this term will go to where? To 0. Simple. What does that mean? That this term, the whole term, will not affect the response very much, okay, as k increases. Now we will think later about this, of course, k. Wow. Another example to show you control, you will see something called insect flying, okay? And number of neurons, you know what is the meaning of neurons? You all have neurons in your brain, okay? Your brain actually consists of neurons, which are the processing devices, okay? Your neurons are the processing devices. You have millions of neurons, but this insect have only around half million neurons, but you have millions, of course. This insect can, and you can monitor it. Scientists actually monitor it over the years to learn from insects, okay? To see how they control their flying. You can see how robust they are, not easily affected. How much control they have over their body, okay? Of course, there are things you have to read about it, and I'm leaving it to you so you can read about how they can see their where they're heading, the obstacles around, if there are obstacles, how it can feels the air dynamics, I mean the pressure of the air. Okay, so it's not everything can be seen. You have other sensors to your body, isn't it? You can hear, you can feel the air coming to you. Okay, you can feel so many things, and this insect actually has to see and feel in order to process and control its wings. Okay, and of course, as I said, they study it a lot, and you can look into the internet and you can see it. Example about the unmanned system. We have so many applications for unmanned systems. We have marine vehicles, that we use in the undersea. We, of course, submarines, but these submarines are what we call unmanned. They go down deep. I mean, deep down under the ocean, where the human body cannot sometimes cope with the pressure. Okay, so we send unmanned vehicles down there, or unmanned submarines down there, and these machines actually are unmanned. There is nobody there inside them, and they actually control themselves. Okay, the time is running. The automatic gear, you know, there are cars with automatic gear. Wow, it's a system that needs to be controlled, and you don't know actually how it works. The lights, the motor, everything. Okay, these things now use computer or computers inside the car to control these things in the new cars. Okay, the other one is, look at this, the human transporter, 2 wheels only, and it must be stable while you are driving it. Look how he's standing. Okay, because it's not easy to talk to somebody sitting on a chair while you are standing. Okay, so he can go up to be in phase with them. The other one here, you can see it is going, how the wheels are adjustable, so he can go into the pedestrian. Also, another example on this vehicle, how he can change it in order to go climb the stairs. Okay, this is a very sophisticated device actually. Modern engineering applications of control, so many applications. Okay, that was the summary. Okay, of course there's, come on. Okay, so that was just the summary. I'm not going to talk, it's over. Now we have more examples, and finally we'll come to the control system.